So this is the flip portion of section or chapter 7.4 on trig substitution. It's a very specific technique that we use when we see integrals containing radicals of the form a squared minus x squared, a squared plus x squared, or x squared minus a squared. So any radicals of these, right, or powers of these radicals. So and or powers of these radicals. It turns out that for any integral containing a root or a power of these three terms of interest, a squared minus x squared, or x squared minus a squared, or a squared plus x squared, it turns out that if we can make a trig substitution to make it a solvable integral. So right now, how can I solve the integral of dx, dx over the square root of x squared minus, or plus a squared. Let's do it that way, plus a squared, right? There's nothing that we could really do. Substitution won't work. So substitution fails. Okay, and also you will notice that it looks something like the trig function of tangent inverse. So it's something like tangent inverse, but that doesn't help us either, because it's 1 over, right, x squared plus a squared. So we need another technique, and that's going to involve these trig substitutions. So whenever you see the root of a squared minus x squared, we're going to substitute with x equals a sine a. Square root of a squared plus x squared, we're going to substitute with a tangent of theta. And x squared minus a squared, we're going to substitute with a secant of theta. So the goal with these trig substitution is to turn a sum or a difference, right? Here we're always either adding or subtracting, and we're going to turn it into a product. And products are a little bit easier for us to integrate with trig functions. So that's where we're heading. So why these substitutions? Why specifically, do we pick, when we see a squared minus x squared, why do we pick sine of theta? Well, the answer lies in the right triangle. So let's look at a right triangle. And I'm going to rewrite it here for sake of argument. Just erase it and start again. So you have a right triangle. Here's your angle theta. Recall that with the right triangle, right, that's your hypotenuse, that's your opposite side from theta, and that's your adjacent side of theta. If we were to put it in terms of a and x, I'll rewrite it here. I'm having trouble on my stylus here. So if this is theta, I'm going to call that a, and that's x. And the question becomes, what is this? Using the Pythagorean theorem, right, your other leg would be the square root of a squared minus x squared. Right, so that's your other leg in terms of a and x. So let's look at the sine of theta. Theta is your angle here. The sine of theta, which is equal to the opposite over the hypotenuse, right? Which in terms of our other triangle right? Opposite, excuse me, is x, and the hypotenuse is a. So solve. Solve this equation, 4x. So you want to solve sine of theta equals x over a. Solving for x, you get x is equal to a sine of theta, which is precisely the trig substitution that we want to make whenever we see, right, x squared, or a squared minus x squared. So when you see an a squared minus x squared, we're going to substitute with a sine of theta. And you could use this argument for tangent and secant as well. But when you see an a squared plus an x squared, we're going to substitute with a tangent of theta. And when you see an x squared minus an a squared, you're going to substitute with an a secant of theta. This all makes sense when we see a problem, but I wanted to pre-expose you to this material before class because I really would just like to go into problems from here. We're going to have a full course on our plate here. So let's move along. We're going to be using and employing the trig identities again. All right, so how are we going to do this? How's the process going to work? We're going to use the trig identities again to help us along the way. All right, we're going to use the unit circle for sure. We're going to use the unit circle and our knowledge of derivatives of trig functions. We're going to use the techniques that we learned in 7.3. So we're going to use the 7.3 techniques, and as always, we're going to use our algebra to keep things as simple as possible. There's one more identity back here. You've been working with these identities. You know, we're getting used to the half angle one. Certainly that one probably needed dusting off. But you absolutely have been using the reciprocal identities and the Pythagorean identities. So now we're going to add another grouping of identities that we're going to be using, and that's the double angles. So we're going to need to work with these identities in addition. Again, I'll provide the trig identities on an exam, but you should be, and I will give you, I think I'll just print off a copy of the formula sheet that I'll use on the exam, and I'll give it out in class. You should have that sheet alongside of you when you go to do a problem. Okay? I'm going to try and expose you to one simple problem first, and then we'll do more in class. So I would like to start with, I think, a definite integral. So we've got a definite integral that looks like this. And I'm sure, you know, your mind goes to substitution. It doesn't work. This looks something like inverse sine, but not quite. You know, I would encourage you to employ the trig substitution. So we're going to use trig substitution. Going to use trig substitution. Actually, this is, I'm trying to think. Yeah, let's keep going. So we're going to let x equal a sine of theta when we see an a squared minus an x squared. Right? That's your a. And it's 5 squared. So x, the substitution that we're going to make, is 5 sine of theta. So we're going to move from x to theta, and then we're going to have to go back to x. in a definite integral, we don't need to worry so much about this step going back because we're going to do substitution of the upper and the lower limit. But when we have an indefinite integral, we're going to have to go back from theta to get into terms of x. So let's work on, so that's your first step. You're going to decide on your trig substitution. Take the derivative, and you get 5 cosine of theta d theta. So let's work on the root now. I'm going to pull it aside to work on the root. It helps to minimize clutter and keeps the algebra clean. So this is 25 minus, I'm going to substitute in for, you know what, let me just rewrite it. I'm going to substitute in the next step for x. So this is 25. X is equal to 5 sine of theta. I'm going to put it in place of x, and I need to square it. So algebraically, this becomes this when I apply the power to both factors. I'm going to factor out a 25, and I'm left with 1 minus sine squared of theta. I'm going to make a substitution, and hopefully you recognize that this is just cosine squared theta. So I'm going to put cosine squared theta in there, and when you take the root of that, it becomes 5 cosine theta. All right, so all that I did here was just work on the root in the denominator. All right, but effectively what we did here, and I mentioned this in the earlier slides, it's what we did here was we actually took a term that was added or subtracted. Right, in this case it was subtracted, and it becomes a product, which will be easier for us to work with. All right, that's always the goal, to get to an easier integral. So let's make the substitution on the original. On the original integral. So it goes from 0 to 5/2. Remember, this is x equals. In fact, I think I'm going to put that so that you recall, because we're going to have to convert our limits. This is x equals 0, x equals 5/2. And I'm going to substitute in for the denominator that we just solved, right, which is 5 cosine theta. Dx is actually 5 cosine theta d theta. All right, so we're making a substitution, and then we're going to integrate. But here we've got mixed pieces, right? We have our upper and lower limits in terms of x, but our integrand, and we're integrating with respect to theta. So the mix needs to get cleaned up. We'll have to clean up the limits of integration. So let's algebraically reduce this. It cancels out, and you're left with x equals 0 to x equals 5/2 of just simply d theta. So that's an easy integral. I think everybody would agree it's just theta. But we need to realize that we've got these pieces in terms of x. All right, so I'm going to work on those limits of integration for now. So the sine of theta is equal to x over 5, based off of our substitution. All I did was just solve for sine of theta. Theta is equal to sine inverse of x over 5. And again, all I did was solve for theta in this equation. substituting in for x, we're going to work on the upper limit first. This becomes inverse sine of 5 halves over 5. So this becomes sine inverse of 1/2. So think of a unit circle at this point. So here's where we're using all these different pieces. Here's the unit circle piece. Right? What angle has its sine equal to 1/2? So what angle has its sine equal to 1/2? And your answer is, right, sine is y over r. So where is y equal to 1/2? It's equal to 1/2 at pi over 6. All right, so that's your upper limit. Let's work on your lower limit. All right, so for your lower limit, theta is equal to the inverse sine of x over 5, and that's equal to the inverse sine of 0, and that happens at 0. So your new limits of integration in terms of theta, theta equals 0, and theta equals pi over 6 d theta. Now we've got a nice integral in terms of theta, and our limits of integration are in terms of theta. Taking the antiderivative, that's just theta. Evaluating it between 0 and pi over 6 is just pi over 6 minus 0. So the answer to this integral is pi over 6. And again, when we have an indefinite integral, we're going to need to use a reference triangle to get back to x, right? Because the integral is in terms of x. So in summary, let me just summarize here so you understand what we did. Right, we just found the integral from 0 to 5 halves of dx over the square root of 25. This isn't working right. My eraser's failing to work. There it goes. Gotta love technology when it works, right? So, that's your integral. That's your answer to that integral. So that ends the flip portion of the classroom for 7.4. When we meet in the classroom, we're going to strictly be going through problems using all of the 3 different substitution techniques and a kind of blending of methods from 7.3.